Hi everyone, welcome back. Now we're going to get into solving non-homogeneous recurrence relations. That's going to be our topic of discussion for lecture 14, in which case we'll focus on first order recurrence relations, and lecture 15, where we'll focus on second order recurrence relations. Much like we did for homogeneous recurrence relations, we'll come up with ad hoc techniques for solving the first order ones, and then general methods for the second order, which also work for first order and higher order as well. So today is just going to be focusing on ad hoc techniques. Given the particular form of the recurrence relation that's first order, let's figure out a way to solve it. So before we get into those solution techniques, I have a problem here. It's the Towers of Hanoi problem, which you may or may not have heard of. So it's a puzzle. You've got some discs on a pole, and the goal is to move those discs from one of the poles, in this case pole 1, over to another pole, we'll say pole 3. And there's only two rules. It can only move one disc at a time, and a larger disc can never land on top of a smaller disc. And what we're interested in is how many moves are necessary. So in other words, what is the minimum number of moves required to move all the discs from post number 1 to post number 3. So here's example of the Towers of Hanoi puzzle. We've got these discs, and I can move it from one pole to another pole. If I move a disc that's larger, I can't put it on top of that one, so I can only maybe move it over to that pole. And the idea is to try to move all of the discs to another pole. So for example, if I remove these two, and I just focus on the 2-disc version of the problem, we can see we've just solved it. We can move this disc there, we can move the big disc onto pole number 3, and the small disc on top of it, and there we go. And we just count up the number of moves it took. Our goal is to try to come up with a method for determining what is the smallest number of moves to solve this puzzle for n discs. So what is the smallest number of moves for n discs? And I'll leave you to just ponder that for right now. You can think about it. We will solve it at the end of this lecture. This will be one of the examples we do, but you could pause the video and take a moment to try to think about how you would solve it yourself. Alright, so let's get into our examples. So here is an example of a first order, linear, constant coefficient, non-homogeneous recurrence relation. So we can see it's first order from this bit over here, and then non-homogeneous because they're on the right hand side is some function of n, and we're assuming it's non-zero. There's also an example of a second order one here. We're not going to focus on solving these in this lecture. That'll be lecture 15. So how would we solve a recurrence relation of this form? Well, let's just focus on the particular case where that constant c1 is -1. We'll take that as our starting point. So if that's the case, then our recurrence relation can be written as an is equal to an minus 1. So notice when I took c to be -1, so there's a negative in front of the a sub n minus 1, it means I can just move it to the other side of the equality and get a plus sign in front of it. So that's what I've done over here. I've just moved it over to the right. And so there's how we can write our recurrence relation. And that's the thing I want to solve. So how are we going to solve it? Well, we're going to proceed like we did in the homogeneous case. We're going to write out the recurrence relation for a given value of n, and then we'll write it out for the smaller values as well. And then we'll sum up these equations. So there's a couple, and then we'll get down to a2 is equal to a1 plus f of 2. a1 is equal to a0 plus f of 1. And we're not given an initial condition in the question, so though we can just assume that this is some constant value. A0 is just some constant. It's our initial condition, whatever that would be. So I'm not going to write an A0 equation down below because I wouldn't use the recurrence relation to get it. This is just going to be given as the initial condition. So there's all my equations that I have, and what we'll do is we'll sum them. So we'll sum these. And the nice thing about summing them is if I add up everything on the left and everything on the right, there's a lot of common terms on the left and the right. So there's an an minus 1 that appears on the right. It also appears on the left, so they'd cancel. An minus 2 would cancel. All the way down to a2 that would cancel. And then a1s would cancel. And so summing these equations would just boil down to an is equal to a0 plus f1 plus f2 plus ... all the way up to fn. Or shorthand, we can use summation notation, which is the sum from I equals 1 to n of f of I. And so what that means is, in order to solve the recurrence relation, we just need to figure out what this sum is. So to solve the recurrence relation, we just need to know this sum. And it turns out we actually do know quite a few sums that we could work out the closed forms for. And we'll review those over this lecture. So let's have a look at a specific example. So here we are interested in the same left-hand side, an minus 1, but here our function is 3n squared. So that is our f of n. So from above, from our comments or remarks above, we know that an is equal to a0 plus the sum of fn, actually of fi I should say, because we're going to sum over these, sum of fi, where I goes from 1 to n. In this particular case, fi is 3i squared. I goes from 1 to n. I can factor out that 3 from all of those terms in the sum, and it just boils down to the sum of I squared. And our remarks from above said we can therefore solve the recurrence relation if we know the value of this sum. And in this case, this is the sum of consecutive squares, and that's something we do know. We do know that it is n times n plus 1 times 2n plus 1 all over 6. And so this reduces down to, so a0 is 7, a 3 in the top can cancel with a 3 factor in the 6 in the denominator, and I get that it's n times n plus 1 times 2n plus 1 all over 2. And so there we go. We've solved it. Okay, it depended on knowing a fact. So the fact we needed was the sum of consecutive squares from 1 up to n is n times n plus 1 times 2n plus 1 all over 6. So that was a fact we needed. Where would we learn such facts? Well, these come up from time to time in various courses. So this one you may have seen in Calculus 2. It gets used quite a bit there, sum of consecutive integers. But if you haven't taken Calculus 2, not to worry. This is a fact that we'll also develop in this course as well. We just haven't got to it yet. So I am using it before we've actually proven it in this course, but that's fine. We'll treat it as a fact now, and then we'll verify it later on once we have the appropriate tools. But that's what we've used here. At the end of this lecture, I'll actually summarize a number of the summation formulas that are worth knowing because they do come up time and time again. And this is one of those ones that I've summarized. If you have the notes in front of you, you just flip to the end of this lecture and you'll see a number of those summation formulas that I've listed there, along with various proofs of them, except for this one. I've deferred the proof till later on. Okay, so there is basically a summary of what we're doing this lecture. We are solving first-order recurrence relations by using the technique of what we call iteration, writing it out and writing it out again for a lower value of the index and a lower value, summing them all up, getting some cancellations, and getting a formula. The formula requires we know how to evaluate a certain sum that comes out in the end. In this case, it was the sum of consecutive squares. Let's have a look at another example. Now, the next example has a negative 3 in front of the an minus 1. Our previous one was a negative 1 there. What's the difference? Well, the difference is we've looked at this, what we've called case 1, and that is when C1 is equal to -1, and that allowed us to rewrite the recurrence over and over again for smaller values of the index and get that cancellation that happens. This method's not going to work as written here when C1 is not equal to -1. However, we can slightly modify it so it does work, and that's what we're doing in this next example. How do we slightly modify it so it does work? Well, again, we do the same thing we just did. We'll write out the recurrence relation. I'll keep an on one side, I'll move the n-1 to the other side, and along with the fn. So there's our recurrence relation. Now we'll just rewrite it out again with the lower value of the index. So an-1 is equal to 3 times the previous one, so 3 times an-2, plus 5 times 3 to the value of the index, n-1. And I'd like to do this over and over again. So maybe I'll do one more, just so we can maybe spot a pattern, and then ... and then we'll write out some of the smaller values. So we got an-2 is 3, an-3 plus 5 times 3 to the n-2. Now I'd like to sum these all up. The problem is if I sum them all up, I'm not going to get that nice cancellation I had. The reason I'm not going to get that nice cancellation is because I have 3 an-1s on this side, but only one of them over here. And I've got 3 an-2s on this side, but only one of them here. So instead, what we do is we just scale through the second equation. So I'm going to multiply everything by 3, because I want that 3 in front. So if I multiply by 3, then that gets multiplied by 3 to give me a 3 squared. And this gets multiplied by 3. So maybe I'll put the multiply by 3 out here. And so we could write this as 3 squared an-2 plus 5 times 3 to the n. And just to see that there's a pattern that's going to emerge here, we'll do that for the earlier one. That's 3 to the 1, an-1 plus 5 times 3 to the n. And now what about the next one? Well, now I'm looking at summing up all these equations, but in this one I have 3 squared in front of an-2, and this one only has a 1, so I need a 3 squared in front of it. So I multiplied this equation by 3 squared, and that becomes a 3 to the 3. And then I multiply by a 3 squared here. So I'm just scaling through that whole equation by 3 squared, so this becomes 3 to the 3, an-3 plus 5 times 3 to the n. And now we're starting to see a pattern emerge, that we've got a 3 to the power of 1, a to the n minus a sub n minus 1, 3 to the power of 2, a sub n minus 2, 3 to the power of 3, a sub n minus 3. And these sides are all the same, 5 times 3 to the n. So if we continue on, then we'll get down to the equation a sub 2 is equal to 3 times a sub 1 plus 5 times 3 to the 2 in this case. And then I have to think, okay, what did I want in front? Well, I just follow the pattern. What's going to be sitting in front of the next term? Well, I look at these two and I say, a sub n minus 2, I get a 3 squared. So I need an n minus something to give me a 2. And whatever that something I'm taking away from n that will leave me with a 2 is the power that I'm putting on the 3. So that's going to be a 3 to the n minus 2. And then this will be a 3 to the n minus 1 because it's one more than it. And then this would be a times 3 to the n minus 2 because the product of them was going to give me the 3 to the n. So I'm just matching the pattern here, and so this becomes a 3 n minus 1 a sub 1 plus 5 times 3 to the n. And then lastly, we'll do it for a sub 1. That would have a 3 n minus 1. And then we've got a 3, and this will be an n. And then we've got our a sub 0 plus 5 times 3 to the power of 1 times 3 to the n minus 1. And that becomes 3n a sub 0 plus 5 times 3 to the n. And we also have that a0 is equal to 2. So that's something I could use here. I could use the fact that a0 is equal to 2 as my last equation. In the previous equation, because I'm wanting these things to cancel, I notice that there's a 3 to the n times a0. So I'd want a 3 to the n in front of it, and then I'd want a 3 to the n being multiplied to that. And so now what I've got is, if I focus my attention on all of these things, I'm going to add up all of those, including this one that's hiding over here. I'm going to add up all of these. That'll be my right-hand side. I'm going to add up all of these. That'll be my left-hand side. But I see I get lots of cancellation. I get that cancels with this cancels with this cancels with something in the dot, 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 something in the dot, 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 cancels with that. And then this cancels with this, and this cancels with this. So the only surviving terms that we get are all of these, this one, and this one. That's all that survives. So what we're going to do is we're going to sum these, and we get an is equal to 2 times 3 to the n plus 5 times 3 to the n, being added up how many times? Well, how many instances of it are here? It's easier to count by looking at the equation. So 1, 2, all the way up to n. So there's n equations there that have that. So there's n of these. N of these. And so that means we get a multiply by n there. And there we go. We've found our solution. It's a common factor of 3 to the n in each of those. So it's 2 plus 5 times n, 3 to the n. And that's an. And so there we go. We have solved that recurrence relation. We could check to make sure it is a solution. So what would we do to check? Well, we check a sub 0. That would be 2 plus 5 times 0 times 3 to the 0, which is 2 plus 0 times 1, or 2. Excellent. So it satisfies the initial condition. Does it satisfy the recurrence relation? Let's check that too. So we want to plug it in. So we want to plug an minus 3, an minus 1, and see if we get 5 times 3 to the n. So we plug that in. That's a 2 plus 5n, 3 to the n, minus a 3 times 2 plus 5 times n minus 1, 3 to the n minus 1. Does this work out? Well, what we see is we get a 2 plus 5n, 3 to the n, minus that 3 can multiply over here to make that a 3 to the n as well. So we get a 2 plus 5n minus 5, 3 to the n. And we would get a number of things canceled. We get this 2, 3 to the n cancels with this 2, 3 to the n. We get the 5n cancels with the negative 5n, 3 to the n. And so there's only one survivor there. And it is the negative 5, 3 to the n, or 5 times 3 to the n. And so, yeah, it also satisfies the recurrence relation. So there is our solution. And we've double-checked that it is our solution. So this is our ad hoc technique for solving first-order non-homogeneous recurrence relations. And it involves being able to do the sum of the function fn that's on the right-hand side, that non-homogeneous part. In this case, the sum was quite nice because it was just the sum of n things that were all the same. So now we'll consider a couple more examples. So we're coming to the towers of Hanoi problem. In this case, what we want to do is we want to move all the disks from pole 1 to pole 3. And the way we're going to do it is we're going to think, so we want to do it optimally, so we want to do it with the least number of moves. So we're going to think, how can I make this a recursive procedure? Because I'm trying to build a recurrence relation from it. So the idea is as follows. Let's consider the top n minus 1 disks. Those top n minus 1 disks, I can move them here. That's step 1. It'll take me some number of moves to do that, and I'll probably use pole number 3 in the mix as well, but the idea is I can do some sequence of moves that'll move all those top n-1 disks to pole number 1. Once I've done that, I've freed up this bottom disk. So then I can take that bottom disk and I can move it over here. So that's my second step. And then the third step would be to move those n-1 disks on top. And that's what's listed there. Step 1, move the top n-1 disks from pole 1 to pole 2. Then move the nth disk on pole 1 to pole 3. And then step number 3 is move those top n-1 disks from pole 2 to pole 3. How many moves would this take? Well, if we let m sub n be the number of moves to successfully move those n disks, then the number of moves that it would take to do our procedure here is as follows. We want to move the top n-1 disks. That would take m sub n-1 moves. Then we want to move the bottom disk over to pole 3. So that's just one move. And then we want to move the top n-1 disks to pole 3. That's again another m sub n-1 moves. So that's our recursive procedure. Do the sequence of moves we need on the top n-1 disks, however many that takes, that's what we call m sub n-1. Then move the bottom disk, and then move the top n-1 disks again so they're sitting on top of the bottom disk. We want to determine and solve a recurrence relation for this number m sub n. So let's get a feel for what it is. M sub 1. If there was only one disk, well, then it would take one move. We just move that one disk from pole 1 to pole 3. How about m sub 2? If there was two disks, let's just get a picture drawn here. So there's disk 1. Well, maybe I should call that disk 2 because I think I'm calling the larger ones the higher numbers. So we got our large disk and our small disk. I want to figure out how many moves it takes to solve this puzzle. Well, I'll take the small disk and I'll move it here. And then I'll take the large disk and I'll move it over here. So that's move 1, move 2, and then move 3. And we've solved the puzzle. And so that's 3 moves. So what about to move the n disks? Well, to move the n disks, we have those written out. We move the n-1 disks to pole number 2. Then we move the last disk, and then we move the n-1 disks on top of it on pole number 3. And so let's just indicate what we've done here. This was step number 1. This was step number 2 above. And this was step number 3 above. And so our recurrence relation becomes 2 m sub n-1 plus 1. So that's our recurrence relation we want to solve. This is it right here. M sub n is equal to twice m sub n-1 plus 1. So let's solve the recurrence. So we'll do it like we've done in the previous examples. M sub n is equal to 2 m sub n minus 1 plus 1. What is m sub n minus 1 equal to? Well, that's equal to 2 m sub n minus 2 plus 1. But remember, our goal is to sum these things up, because that's going to be our technique for solving them. And in order to sum them up, I'd like this term to cancel with this term, which means I need a 2 in front. So I'll multiply the second equation by 2. So that would become a square there. And then we'll have a 2 to the power of 1 here. Maybe I'll put another 1 in here. Sometimes it helps if we write a couple of equations just to spot what the pattern is. M sub n minus 2 is equal to 2 m sub n minus 3 plus 1. I need a 2 squared in front of this one now, because I have a 2 squared in front of the mn minus 2 above. So that means I'm multiplying that equation through by 2 squared. So this would become a 3, and this is a 2 squared. That's probably enough to start to see what the pattern is. So I know I'm going to have an M1 there. I'm going to have a 2 in front of it. I'm going to have a 1 here. And what are these values? Well, you focus on the one that's probably easiest to see. In fact, they all look like they're giving me the same information. So I look at either the exponent here or the exponent here. They're really the same, or this is just one more than them. So I'm going to focus on this exponent and say, when I take n minus 1, I get a power of 1 there. N minus 2, power of 2. So n minus what gave me this 2 here? Well, that would be an n minus 2. So this is a 2 to the n minus 2. And then this would be an n minus 1 and a 2 to the n minus 2. And then we've got our m sub 1. M sub 1, that's our initial condition. So that's equal to 1 here. And in order to get it canceling with this, I'm going to multiply it by a 2 to the n minus 1. So we get a 2 to the n minus 1 and a 2 to the n minus 1. And there we go. We've got all our equations all ready to go to be summed. So we will sum these. When we sum them up, we get that cancels with that, that cancels with that, that cancels with that, and so on down the line. I always like to do that last equation with the initial condition because it allows me not to have to really think too hard at this stage, because I'm just like cancel, 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 cancel. There's one thing that survives on the left. There's a bunch of stuff that survives on the right, and I just have to collect those together. So what survives on the left is an m sub n. What survived on the right is a 1 plus 2 squared plus all the way up to 2n minus 1. That's a geometric series. We know what the sum of a geometric series is. In this case, it's going to be 2 to the n minus 1 all over 2 minus 1. And in this case, we've now solved the problem. 2 to the n minus 1 is the number of moves, the minimum number of moves it takes to solve the towers of Hanoi problem. Moreover than that, we actually have a method for solving it. It's a recursive method. Move the top n minus 1 disks, and then the bottom one, and then the top n minus 1 disks again. And so that's a recursive procedure. So then we just have to worry about how to move n minus 1 disks. Well, we can do that by moving n minus 2 disks, and then the nth minus 1st disk, and then the n minus 2 disks. So we have a recursive procedure, and that recursive procedure also allowed us to count. So I've written down geometric series here. Let me just indicate what it is that we've actually used. So in this case, if we've got k equals 0 to n of a to the k, in this case, a was equal to 2. I can sum up to n minus 1, but you might be more familiar with it if the sum goes up to n. This becomes a to the n plus 1 minus 1 over a minus 1. So that's our general sum of a geometric series. In this case, our sum only went up to n minus 1, so that's why we had a 2 to the n in our exponent there, because it was whatever the upper value of the thing being summed over, the k value, it got summed up to. In our case, it got summed up to n minus 1. So this is just one more than that last exponent, and so it was n in our case. I will justify this formula at the end of the lecture. We'll go over some of the summation formulas, but right now I'm just using it as a fact, and I'm drawing on the fact that you probably will have seen this somewhere before, probably in high school, and then again in calculus if you've taken it. So now that we have our solution, we can go ahead and just make sure it seems reasonable by doing a few reality checks. So let's check. What is m sub 1 based on our formula? Well, that's 2 to the power of 1 minus 1, which is 1. That's good because we saw that it only took one move to solve the one disk problem. What about m2? Well, that would be 2 squared minus 1, which is 3. So both of those work out and give us the values we expect. And in general, it's 2 to the power of n minus 1 is the number of moves. So now let's have a look at the next example. So in this example, we've got a loan that's being taken out. The loan is for S dollars, and every month Pauline pays back P dollars, and the bank charges her an interest rate of R% every month. We're going to let AN be the amount she owes after n months. We want to determine and solve a recurrence relation for that quantity, A sub n. So maybe we'll think about the small cases first. What's A sub 0? Well, A sub 0 is the amount she owes after 0 months. Well, she just owes S dollars because that's what she's taken out. There hasn't been interest occurred on it because interest will get incurred after the first month. So what about after n months? Well, after n months, what does she owe? Well, she owes whatever she owed last month plus whatever interest gets incurred on what she owed last month minus whatever her payment is. And her payment is for this month, so we'll indicate here where these are coming from. Amount owed, or maybe I should say amount still owing after last month. This is the interest on amount owing. And this is the payment made. This month. And now after n months, that's what she owes. She owed whatever she still owed from last month, plus the interest, minus whatever she paid off this month. And so there is our recurrence relation. And rewrite it as a 1 plus r, a n minus 1 minus p. And so this is what we want to solve. So how are we going to solve this? Well, our solution, again, the same technique we're using. I'm calling this our ad hoc technique because it's our technique for first order linear recurrence relations with constant coefficients, which are possibly non-homogeneous. And this one's non-homogeneous because of this non-zero term there. So the way we solve this is we write out the recurrence relation, and then we write it out again and again and again, and then add them all up to get the cancellation. So this is our recurrence relation for index n. We go for n minus 1. So that's n minus 2 minus p, and so on. But now we just have to figure out what do I need to adjust by. Well, when I add these up, I need this to cancel with this. So I need a 1 plus r in front of it here. So I need a 1 plus r here. So I'm going to multiply that equation by 1 plus r. That means I get a square there and a 1 plus r here. Now I could think of this in the previous case as a 1 there and a 1 plus r to the 0, and I'll make that a 1, just to start to see a pattern emerging. In the next one, we've got an a sub n minus 2. We've got the recurrence relation tells us that's 1 plus r times a sub n minus 3 minus p. Now I need to adjust. So I'll multiply by 1 plus r all squared there. The reason is because I have a 1 plus r squared in front of the a n minus 2 here. So I need to make sure I match it with something on the left-hand side. And when I do that, it means I'm multiplying by a square. So that becomes a 3, and then I get a 1 plus r all squared there. And then we just keep going. Down to a sub 2 is equal to 1 plus r, a sub 1 minus p. What are our powers? And this is a 1 plus r. This will be an n minus 2. This will be an n minus 1. This will be a p times 1 plus r to the n minus 2. And then we also have the 1 for a sub 1. A sub 1 is equal to 1 plus r a sub 0 minus p. And then I've got to scale through. I scale through by a 1 plus r to the n minus 1. That becomes a 1 plus r to the n, a 1 plus r to the n minus 1. And then lastly, I've got an a sub 0, but that is equal to s. And I will scale through just so I can sum them up and get the cancellation I want. So there we go. We've just written out a bunch of copies of our recurrence relation with various scaling factors. And so now we're going to sum these. What happens when we sum these up? We get a lot of cancellation. As usual, all these things cancel off. The surviving terms are this one, and all of these. And so we get an is equal to 1 plus r to the n times s minus p times the sum of 1 plus r to the k, where k goes from 0 up to n minus 1. And so that's a geometric series again. So we get a 1 plus r to the n, s minus p. Geometric series, that becomes a 1 plus r to the n minus 1 over a 1 plus r minus 1. And so I'm just indicating here that we've just used the fact that it's a geometric series, so we know its sum. And so this becomes 1 plus r to the n, s minus p, 1 plus r to the n minus 1, and then all of that is over 1 plus r minus 1, so that just becomes an r. So I'll clean this up a little bit, and I'll just indicate that that's over an r there. This I will just move down a little bit. We've got some parentheses here. And so I've got one term, actually two terms with a 1 plus r to the n in it. So 1 plus r to the n, s minus p over r, and then I've got a plus p over r. And there we go. We have found our solution. And this is when n is greater than or equal to 0. So there is the amount owing after n months for any given n. You can check, just a quick reality check, does it work for n equals 0? When I get n equals 0, I get s minus p over r plus p over r, which reduces down to s. So yeah, quick mental check, a sub 0 is s from this formula, and it gives us all of the values for n as well. All right, so that's it for the examples. The last thing I just want to touch on is the summation formulas that we've been using, and some that we haven't actually used yet, but we will as well. So these are all the useful summation formulas that we've used in this lecture. If you're familiar with them, then there's nothing more to really watch here. I am just going to justify why some of these are true, and maybe these justifications will be different than the ones you're used to seeing and might help in seeing why some of these are true from a discrete math perspective. So that's it for this section. Thanks very much for watching, and we'll see you again next time.